Hello and welcome to this morning's lesson, which is on pulleys. So, first of all, let's go over what a pulley is. So, a pulley is a wheel on which a rope or string or cable, for the purpose of mechanics, is two particles hanging either side, which is either horizontal or vertical. So basically what we've got here is we've got a pulley, we've got two strings which are acting like this, and then as this one comes down, it's going to pull this one up, or sometimes you're on a horizontal plane, and as this one pulls down, it's going to pull this one along here, like so. So the first thing it says here is, why can't we just model both particles as a single particle the same as before? Now the reason for this is that the particles are moving in different directions, and the tensions are not the same throughout because of this, which means that they do not cancel. Now, when you're doing mechanics or M1, the tensions are the same. So it says here next up, so what are the conditions in which the tension is the same? And the conditions of this is if it's a single piece of string and then we're connected with a smooth pulley and it's an inextensible string, which means that the tension is going to be the same throughout all of this. Okay, so let's have a quick look at this first question here then. So the first question here says, a pulley is a particles P and Q of masses 2m and 3m are attached to the ends of a light and extensible string. The string passes over a small, smooth pulley, and the masses hang with the string taut. The system is released from rest. Write down the equation of motion of P and Q. Find the acceleration of each mass. Find the tension in the string. Find the force exerted on the pulley by the string. Find the distance moved by P in the first 4 seconds, assuming that P does not reach the pulley. So the first thing that we need to do with this type of question is to draw a picture. Okay, so here we've got a ceiling or a roof or something that the pulley is attached to. We've got our pulley, which is here like so. We know that this is attached to this. We've got our string coming over like so. And we've got two particles here, one which is 2m and one which is 3m. So here we've got the mass of this. It's worth noting at this stage that it's given us it in terms of m, so 2m and 3m, which basically means that the ratio of these particles is 2 to 3. Now it doesn't matter what that m is, because at some point they will cancel out, and we'll see that later on. So the weight of this one here is going to be 2mg. The weight pulling down on this one is going to be 3mg. Now, because this pulley is smooth and this is an inextensible string, we know that tension is going to be the same throughout all of this. So the thing which is stopping this particle from falling due to gravity, from falling at the speed of gravity, is the tension which is there. The thing which is pulling down on this pulley is this tension here. We've got the thing which is pulling down on this pulley here on this side, which is also that same tension, and then here we've got the tension which is pulling up this particle. So we've talked about the fact that we have accelerations on both sides of this. Now, what we need to think about is that as this comes, well, first of all, this one here is heavier, so it's going to be moving this way around. So as this one falls down, it's going to pull this one up. And because these tensions are the same throughout all of them, it means the acceleration on both sides is going to be the same as well. So this one is pulling it down, this one's pulling it up. So the acceleration for this one is acting down. The acceleration for this one is acting up, like so. The acceleration of this one's pulling down, the acceleration of this one is pulling up. Okay, so that's our diagram drew. So now what we need to think about, in fact, let's put these up. That one there, that one there. You've got a diagram which is there like so. So, let's have a go at part A then. So part A, So we're going to be thinking about, we should label these first. Which way round is that? Again, P and Q. So first of all, we're going to be talking about P, which is here like so. So let's label this one here as P. Like so. So we're looking at particle P first of all. We're looking at it on its own. So we're resolving this acting up, like so. We want to write down here, we're going to be using F equals ma. So force is equal to mass times by acceleration. So what are the forces which are acting on P here? Well, we know that acceleration is acting up, so we're going to be taking that direction upwards as positive. So we've got here the tension here, which is pulling this up. So it's going to be T. We've got this, which is holding it back, so minus 2 mg, which is equal to, so this is the forces, the mass of this one, which is 2m, times by the acceleration, which I don't know, which is just a. So that's for P. Next thing we're going to look at is Q. So it says here, write down the equation of the motion for P and Q. So this one here is Q. So what are the forces which are acting specifically on Q? So first of all, we're going to write them, we're resolving with this one acting down. And this is F equals ma that I'm using, same as always. So what are the forces which are acting on this? Well, acceleration is acting down this time, so that's the way I'm going to take as positive. So it's going to be this one here, which is positive, so it's the other way around this time. So 3 mg minus the tension is equal to the mass of this, which is 3m, times by the acceleration, which is the same in both of these, which is a. So that's part A done. So the next part, part B, in fact, let's just check that, make it big for you. Show you here. So the next part here says, find the acceleration of each of the masses. So we've got to do this by resolving. Now the thing that we have the same in both of these is T. So it's worth making them both equal to T, and then make them equal to each other. So the first thing, let's call this one here 1. Let's call this one here 2. Let's write 1 over here. So I'm going to have T minus 2mg is equal to 2ma. Let's have that one there. I'm going to have this one here, 3mg minus T is equal to 3ma. I want to make them both equal to T. So this is my first one here. So let's take this 2mg over to the other side. So that's going to be T is equal to 2ma. I'm adding that 2mg, so it's going to be plus 2mg there, like so. With this one here, I'm going to take that T over to the other side. So 3mg is equal to 3ma plus T. Take the 3ma to the other side, so 3mg minus 3ma is equal to T. Now, because they're both equal to T, we can make them equal to each other. So it's going to be 2ma plus 2mg is equal to 3mg minus 3ma. So next up, we notice that there's an m in all of these. So we can cancel out that m. So 1, 2, 3, 4. There's an m in all of them. So that just leaves me with, here, 2a plus 2g is equal to 3g minus 3a. So I'm going to take this 3a over, I'm going to bring this 2g back, so I end up with 5a is equal to, minus this 2g is going to be equal to just g. So divide by 5, let's do that over here to leave some space. So a is equal to g over 5 meters per second squared, like so. So that's that first part done. Does it say, we'll probably write this in terms of, into 2 or 3 significant figures first of all. We'll leave it in terms of G for now. So part C says, find the tension in the string. So to find the tension in the string, we go back to one of these, and it doesn't matter which one we go back to because they are their tension's the same throughout. So in fact, it's probably easy to go to one of these ones here actually. So we've got to find this in terms of M. So let's pull this up a little bit here. I'm just going to fold this up. So we know from what we've just done, now this is part B, so we're doing part C now. Let's do this over here. So part C, find the tension in the string. So we're going to use this one here. Tension is equal to 2ma plus 2mg. We've just worked out that our acceleration is equal to g over 5. So my tension is equal to 2m times by g over 5 plus 2mg. So I end up with here, T is equal to 2mg over 5 plus 2mg. Let's write this one as over 5 as well. So it's going to be T is equal to 2mg over 5 plus, if I want this over 5, it's going to be 10mg over 5. So we're going to end up with here 2mg over 5 plus 10mg over 5, so then my tension is equal to 12mg over 5. It is in terms of m, don't worry too much about that. The units on this are equal to newtons. Okay, so that's part C there. Part D says find the forces acting on the pulley. So if I just go back to this picture here, this is the pulley here. So what are the forces acting on the pulley? Well, if you look here, on this pulley you've got 2 forces, both acting in the same direction, both acting down like this. So with this one here, what you need to do is if you want to find the forces on the pulley, it's going to be 2 lots of T, 2 lots of that tension. They're the only things which are acting on this. I mean, there is a force holding this up here. Okay, that's stopping it from falling. Okay, but this is fixed, it's not moving, so that means that force up is acting, the force up is the same as those 2 forces acting down. So here we can say, let's just get that one up for you. So here we can say for part D, find the force exerted on the pulley by the string. So it's going to be 2 lots of that tension. So here we're going to have 2T acting down. So it's just going to be this one here times by 2. So this here times by 2 is going to be equal to 2 times by 12mg over 5, which is equal to 24mg over 5 newtons. That's that part done. So the last part here says find the distance moved by Q in the first 4 seconds, assuming that P does not reach the pulley. So let's just talk about that for a second. Why does it say assuming that P does not reach the pulley? So what's happened here is it's saying find the distance moved by Q in the first 4 seconds. So it's saying that this one here is now going to be moving down for 4 seconds. We know what that acceleration is. We've worked out that before, which is here. G over 5. You're going to have to round that at some point. So what we're going to do here is this is moving down, this one here is moving up. Now it says, assuming that this one here does not reach the pulley, and it says that because if this was to reach the pulley, it would stop, wouldn't it? Okay, so or it'd flow over or something could happen to this. So it's saying that it's carry on going down as this was going up for 4 seconds, and this one here is not reaching the pulley. So that's what it's assuming here. So let's have a look at this question. We're just going to consider Q now, so let's just write down what Q is. We've got Q here like so. We know that we've got the 3mg acting down, we've got the tension which is holding it back, we've got acceleration acting down, which we now know is g over 5, and it wants us to do it for the first 4 seconds. So we're going to be using SUVAT here. The acceleration is not gravity. Be careful of that one. My acceleration is acting down, and that's g over 5. Here we've got a time which is 4 seconds. It starts from rest. So we know that u is equal to 0 meters per second. And I'm trying to find out this distance s. So that's what I'm trying to find out. So I'm not involving v. So which one here does not involve v? Well, that's going to be equal to s equals ut plus a half at squared. And actually I know all these values, so s is equal to 0 times by 4 plus a half times by acceleration, which is g over 5 times by 4 squared. So we can put that in our calculator. So s is equal to, that's going to just be 0, 0.5 times by 9.8 over 5 times by 4 squared, like so, equals 15.68. We know we're going to be doing this to 3 significant figures, so 15.7 meters that's going to be. 15.7 meters to 3 significant figures. Brilliant. And that's that question done. Okay. So if you want to look at all the notes, there they are. Remember, you can go back and pause to get all of that down. It is a long question. These are the questions that tend to come up on the paper. These are the ones which are the most likely questions, to be honest. So let's have a look now at another question. So I'll make this big so you can copy it down. Two particles A and B of masses 0.4 kilograms and 0.8 kilograms, respectively, are connected by a light and extensible string. Particle A lies on a rough horizontal table 4.5 meters from a smooth pulley, which is fixed at an edge of a table. The string passes over the pulley and B hangs freely with the string taut, 0.5 meters above the horizontal ground. The frictional force of magnitude 0.08 grams, 0.08 g is that, opposes the motion of the particle A. The system is released from rest. Find the acceleration of the system, first of all, the time taken for B to reach the ground, and the total distance travelled by A before it comes to rest. So again, this is a really common question. So with this one here, we've got to draw this one out first of all. That's the most important part. So here, let's draw this out. It's on a table, so let's draw that table first of all, like so. We've got a pulley on the edge of this table. We've got a particle which is over here. And it says that this is 0.4 kilograms. So there's a force acting down on this which is equal to 0.4 g newtons. There is a a reaction force there, which will be balanced because it's not going through the table. And this is connected over this pulley here to another particle, which is 0.8 here, makes it a little bit longer, 0.8 kilograms. So we're going to be having a force here acting down, which is 0.8 G newtons. Now it does say that it's a smooth pulley, so there's a light and extensible string. So we've got T, which is acting up here, which is going to be stopping this from falling at the acceleration rate of gravity. We've got a tension which is going here, which is acting on this pulley. Now the thing which is holding, we've got another force here, which is another tension, the same tension here, acting this way. And the thing which is pulling this one here is this tension. Now the thing that I'm missing on this one here is the frictional forces, which in this case is 0.08 G, which G stands for gravity there. So, first of all, find the acceleration of the full system. So in fact, it's probably worth noting here that this one here is 0.5 meters, 4.5 meters from that pulley. So this part here is equal to 4.5 meters. And this one here is, how far from the ground does it say? It says that it is, where is it? 0.5 meters, which is there. Worth getting that in there. So, the first thing we've got to do with this is to resolve for both this one and this one. Now, you've got to resolve it in the way that it's going. So we know that this one here is going to be acting down with an acceleration here. And this one here is going to be acting right with an acceleration there. Now, because this string is taut, because this pulley is smooth, because the string is inextensible, these accelerations are going to be the same, and these tensions throughout are also going to be the same as well. So I've got to resolve for both this one acting down, and I've got to resolve for this one acting right for both particles. And what are both particles called? They are called A and B. So this is particle A, and this is particle B. So let's first of all resolve for A. We're going to be resolving for A acting this way. So resolve right F equals MA. So what are the forces acting on this horizontally? Well, the forces which are acting on this horizontally, we're taking this direction as positive because acceleration is acting that way. So what's pulling this particle here? Well, the thing that's pulling it is the tension. What's resisting it? Well, the thing that's resisting it is this frictional force, which is minus 0.08 G. So that's the forces which are acting on A. And this is equal to the mass of this, which is 0.4 times by acceleration. So that's for particle A. For particle B, it's different. For particle B, we're resolving for this acting down. So this is equal to F equals MA. So what are the forces which are acting on this one? Well, the forces acting down on this one are equal to 0.8 G. That's what's pulling it down. What's resisting this, stopping it from acceleration accelerating at the rate of gravity? Well, the thing that's stopping it is this tension, so minus T, which is equal to the mass of this, which is equal to 0.8 times by the acceleration, which in this case is the same acceleration there, which is A. Remember that as these move along here, like so, the acceleration is going to be the same all the way throughout. And then you solve this very similar to the last one you've done. So let's write this one over here. Let's call this one here 1. Let's call this one here 2. So I'm going to have t minus 0.08g is equal to 0.4a. And this one here, 0.8g minus t is equal to 0.8a. So with this one here, we're going to make them both equal to t. So let's add 0.08g, add 0.08g. That will cancel, so you end up with this one here, which is t is equal to 0.4a plus 0.08g. This one here, let's take the t over this side, bring it back, so let's we're going to end up with 0.8g, let's actually do it, plus t, that's going to cancel that one there, so we end up with 0.8a plus t, take away the 0.8a, take away 0.8a, take away 0.8a, so that there will cancel, so you end up with 0.8g is minus the 0.8a is equal to t. So we've got both of these now, both equal to t, so we can make these equal to each other. So we're going to end up with 0.4a plus 0.08g is equal to 0.8g minus 0.8a. Take this 0.8 over, minus this one here. Well, the 0.4a plus the 0.8a is going to be 1.2a, which is equal to 0.8, take away this 0.8, sorry, 0.08, 0.8 minus 0.08 is equal to 0.72g. And then I'm going to divide by this 1.2, so a is equal to that, divided by that. So divided by 1.2 is equal to 3 over 5, 0.6g. And that's going to be meters per second squared. Okay. So with this one here now, we've got that in terms of meters per second squared. We found out what a is. The next part says, part B, it says, find the time taken for B to reach the ground. Okay, now I've drew this on purpose. We've just worked out by resolving the forces what acceleration is. We know that it's starting from rest, and we know that it's travelling a distance of 0.5 metres. Okay, so when we're doing this one here, we're going to be using SUVAT again. So when we're using SUVAT, so S-U-V-A-T, so S is equal to 0.5 metres, U is 0 because it's starting from 0. We don't know what V is. A we've just worked out is equal to 0.6g, and T is what we're trying to find out. Total time taken is yes. We're trying to find out T, so we're not involving V. So which of my SUVAT equations does not involve V? Well, it's the same one as we used before, which is equal to S is equal to UT plus a half AT squared. So let's substitute everything in now. I know that 0.5 is equal to U, which is 0, times by T, which is what I'm trying to find out, plus a half times by my acceleration, which is equal to 0.6g times by T squared. So that's just going to be 0. We're going to end up with 0.5 divided by all of this, which is equal to T squared. Let's do that straight on the calculator, just keep it easy. fraction button first, 0.5 divided by 0.5 times by 0.6 times by 9.8. That's equal to 25 over 147. So t squared is equal to 25 over 147. So square root that. Shift square root the answer, which gives us 0.41. So t is equal to 0.41239. Remember that we are doing this to three significant figures. So t is equal to 0.412 seconds. That's part B done. So just to recap that one, we know that it's travelling 0.5. Let's just show again. We know that it's travelling 0.5 metres down here. We know that the acceleration we've just worked out by resolving these forces is equal to the 0.6 g. We know that it's starting from rest. So we're using the Suvat equations to solve this. Solve this, 0 there, divide by all of this, which gives you this one, and then square root the answers into three significant figures. So, we've got to now do part C. Now part C is the hardest part. Let's go back to this diagram here. With part C, what we've got to think about is the fact that this here is pulling this down for a total of 0.412 seconds. It's pulling this along here. So this here is being pulled along by the tension here. After 0.412 seconds, this here hits the ground. So this here hits the ground. So this travels 0.5 metres there for the 0.412 seconds. Now, once it's travelled, take note, this distance here, the distance it's moving here is the same as the distance it's moving here. Okay, these two distances here are the same. Okay, can't travel further than this. But when this hits the ground, this still is moving. Okay, so what we've got to do is we've got to find out how far it moves along after this hits the ground. Okay, so let's just draw. I'm going to try and draw you a little picture of this so you can see what's happening. Just to make it really clear. So here we've got a particle. We know that it's the 0.4 kilograms. And it's just moved. We know that it's just moved 0.5 metres there, like so. And that's because the other particle has moved 0.5 metres down, like so. I probably should have made this longer. 0.4 kilograms there, like so. So it's moved 0.5 metres. Now at the stage here, where this particle here has hit the ground, this still has some motion. This is still going this way. However, there's something which is stopping this, which is the this motion here. We've got frictional forces which are 0.08 G newtons acting this way on this one. I know that should be attached, but it's just so you can see it there. However, there's nothing here pulling this forward anymore, so we know that it's decelerating. So what we do need to find out is what the velocity is at this stage here. We need to find out how fast this is decelerating, the rate of deceleration. And we know that it's stopping So we know at some point this is stopping. So we know that the final velocity is also v as well. Okay? So here we've got, so first of all, let's find out what the velocity is here. Let's find out what the velocity is when this, when it's not being pulled anymore by the other particle. So let's work out what that is. We can just use v equals u plus at for that. So v is equal to, this is part C, v is equal to u plus at. Well, we knew that the initial velocity of this one was 0. We've got an acceleration which was 0.412 times by t, which we've just, acceleration, silly Billy, is the 0.6 g, and the time was equal to 0.412. So v is equal to u plus at. So I've got these the wrong way around, but we've got our acceleration there, which is 0.6 g, times by our time, which is 0.412. So let's do that one now. So here, 0.6 times by g, which is equal to 9.8, times by 0.412, like so. So the velocity of this here is equal to 2.42256. Brilliant. So my velocity there is equal to 2.42256. Now this here is the final velocity. Let's just zoom in on this a little bit. This here is the final velocity of A as part B hits the ground. So as this hits the ground here, we know that this is the final velocity of this. But at that point there, we know that it's slowing down here. So it's still moving along. It's still moving. But what's happening is it's slowing down. So let's see if I can actually show you this a little bit. So here we've got, in fact, let's use this. Here I've got my hard drive. It's being pulled along like this. But as it's being pulled along, this is pulling it down. And as it's being pulled like that, what's happening is, as I stop and slow down, this is continuing to move. Okay? So as here, we've moved 0.5 meters there. As it's stopped being pulled, it's still got some velocity, so it's still carrying on travelling there. After this 0.5 meters, we know that the final velocity here was 0.42256, which is going to be the starting velocity of this when it's not being pulled anymore. I do need to work out first what that acceleration is at this stage. Okay, so there's the two stages we're looking at there. So we're going to be using F equals ma, so we're going to be resolving this in that direction. We're going to be using F equals ma. There's only one force which is acting on this now, and that force is equal to this force which is acting back, which is the, if I know it's travelling this way, accelerating this way, well, we know it's going to be decelerating, but we know that it's still travelling this way, then the only force which is acting on this one is minus 0.08 g, which is equal to the mass of this, which is 0.4, times by the acceleration, which I don't know. Take note that acceleration is different now because there's nothing pulling it anymore. And there's no tension acting on this anymore because it's hit the floor. So there's no tension acting on this. So here we've got minus 0.08 g. I'm going to divide by this to find out what the acceleration is. So minus 0.08 times by 9.8, all divided by 0.4. So that's equal to minus 1.96. So my acceleration here, which is slowing it down, we knew it was going to be negative, is minus 1.96 meters per second squared. So now we have here we have the initial velocity when it's as it's hit the ground. We know it's slowing down at a rate of 1.96. We know the final velocity is going to be equal to 0. So here we're going to be using SUVAT again. S U V A T. S we don't know. That's what we're trying to find out. The total distance. U I know is equal to the starting velocity of this is equal to the 2.42256. Our final velocity is equal to 0. Our acceleration is equal to minus 1.96. And time I don't care about and I don't know. So which one here does not involve time? Well, that's going to be equal to v squared is equal to u squared plus 2as. So let's substitute everything in now. So I've got 0 squared is equal to u, which is equal to this 2.42256 all squared, plus 2 times by the acceleration, which is equal to this minus 1.96, times by s, which I don't know, which I'm trying to find out. So here now, I'm going to take this s over. I'm going to take this over. So let's multiply these first of all. Let's move this up, aren't I? So 2.42256 all squared is equal to, on this side, 5.868797. This one here is going to be 2 times by the 1.96, which is equal to 3.92. But remember, I'm taking this over to the other side, so that was negative, it's now going to be positive. 3.92 s there. And to find out this distance, I'm going to divide both of those. So 5.868797 divided by 3.925. So this is travelling here. S is equal to 1.49 meters. So I know that S is travelling, but that's not the final answer. Remember, I've got two situations here. One, let's draw them out. One where the particle has moved 0.5 meters here as it's being pulled due to the pulley, but then it's still continuing to move here for another 1.49 meters. So it's still continuing to be pulled there. So as it's continuing to be pulled, we know that we can add both of these together, because it's still going here. So it's going to be this 0.5 here, plus this 1.9, plus this 1.49 here. So it's going to be 0.5 plus 1.49 meters, which is equal to 1.99 meters to three significant figures. Sorry. So we've got here both of these. Let's get these answers up. So we've got both of those answers. We've got somebody at the door there. Don't worry too much about that. We've done it to three significant figures, but actually we need it to. We've done it to three significant figures. They've done it to two significant figures. That's not a problem at all. And that's that question done. Now the hard part of that is the fact that this is still travelling a distance after that. Okay, so I won't get any, you have a go at a question yourself now. We've got 2 pulleys. I'm going to put this on for a second. Copy this question down and have a go at it. Give you a second to do that. Okay, pause to do this. I want you to have a go at this yourself. I'm only going to put the answers up for this one. Just notice you can't see that bottom part here. I'm just going to move that up slightly. So the hardest part of this part here, you're going to resolve all of these forces exactly the same as you've done previously. But the hardest part of this one here is at the point where the it's going further up. So it's exactly the same. This particle here is reaching the ground, but as it reaches the ground, this is continuing to move. So as it stops, it's continuing to move further up. So we know that it's moved a distance of whatever it is at that point here for 1.2 seconds. But then it's still got a velocity there. It's like moving up. It's like it's jumping slightly. So I'm going to put the answers up for these. You should have paused and had a go at this. I'm going to just put this back up here so you can see it. So the first part, part A, is 15 over 4 mg. We find that out by resolving both sides of this, making them equal to each other. So that's the tension there in terms of mg. Part B, we've got K is equal to 3. So K is the mass of that second one, because we know the acceleration of both of these now. So I will solve this for both of these. Part C, well, why is the information how do we usually do the information? We've got a smooth pulley. We're going to say that this one here, that means that this tension is the same throughout. And this last part is notice this last part is 7 marks. So with this one here, we're seeing how far up it travels. So first thing we've got to do is to work out here the distance above the ground first of all, and also the speed, the final speed before it hits the ground. We then know what the acceleration is to this. Well, the acceleration of this is going to be acceleration due to gravity, so 9.8, pulling it down. We know that it's still got some motion. We know that the final velocity is equal to 0, so we're going to be using suvat again. So then once we've worked that out, we're going to add both of these together, which gives you 3.969, which rounds to 3.97 to 3 significant figures, or 4 meters to 2 significant figures. Okay, thank you for watching forces on a pulley. Hopefully you had a go at that last question. You got it right. Thank you for watching and have a lovely day.